Alrighty, so today we're gonna, I guess, do this the old-fashioned way, as Twitch is misbehaving. So we'll just record it this way. Um, let's go ahead and just take a look at what we did last time. We were talking about calculating delta H for a reaction, and we saw two different ways to do it. We could use a coffee cup calorimeter, which is open to the atmosphere. It's at constant pressure. It's made of 2 coffee cups where you will mix your solution inside and measure any temperature changes. And we are able to calculate delta H of the reaction by understanding the mass of our solution, the specific heat of our solution, and the change in temperature of our solution. All that stuff is the numerator. We need the opposite of that because that's all for the surroundings, right? So we need to put a negative sign to make sure that we're talking about the system. And then, in order to kind of standardize it, we divide it by the amount of moles of reactant that we're using. And so that's how we would do it for a coffee cup calorimeter. If we had a bomb calorimeter, things are a little bit easier for us because the mass of the solution and the specific heat are both combined into one term, which is called the calorimeter heat capacity. And so that's something specific for bomb calorimeters. And those are going to be used more frequently in industry. In kind of like general labs, we typically use coffee cups because they're a little cheaper, right? They're just styrofoam cups. We don't need these fancy rigid containers. And so we also would standardize that by using the moles. Just for clarification purposes, technically the bomb calorimeter gives us delta E directly, because if it's at constant volume, again, we can't have any work being done. But since delta E and delta H are usually quite similar to each other, we just go ahead and say delta H. So just putting that out there, you don't really have to worry about it. Okay, so just work with these two. I did mention on Tuesday that we'd have 3 more experimental ways. We're only going to cover 2 of those here. The last one we're going to cover when we talk about Lewis structures in a few chapters. So we're going to have a break from thermochemistry for a little bit, and then we're going to come back to it later. So the first one that we're going to take a look at is Hess's Law. This is one way of combining reactions. So if we know their enthalpy values already for those reactions, we can combine them. And, well, I guess I should be grammatically correct about this, shouldn't I? This could be combined. The reason this is going to be very useful is because it's going to make it so we don't have to worry about doing all these coffee cups and bombs and all sorts of things. So if we already have values that have been calculated by someone else, these are often standardized, we can just take them and use them to our advantage. And we're going to see that generally if we have, let's just do an example of it. I'm going to use one of the examples from our book here, where we have methane burning. Here's our first reaction, methane burning. How many oxygens? 2? Okay. What's important, though, is we do include the states of matter because states of matter do matter for... That's a terrible phrase. States of matter are important when we're talking about enthalpy values. We're going to see later that when we're trying to do phase changes, like solids going to liquids, liquids going to gases, those have a delta H associated with them. They're processes. And we can also think there's an amount of heat related to boiling water, right? We need a certain amount of heat to get water to boil. So states of matter do matter here. So we're going to make some CO2 plus probably 2 waters in gas form because this reaction takes place with high temperature, right? Burning stuff. And then if we take a look at actually, I'm going to leave it like this. gaseous water turning into liquid water, we can actually combine these two reactions, and I'll show you how the work for that. But if we combine them, we can see what the enthalpy change would be for having liquid water as a product instead. Doesn't seem very exciting, perhaps, but it is. We remember that enthalpy is a state function, right? Which means its value is set already. Just it doesn't depend on how you get there. So Hess's law tells us that no matter if a reaction takes place in one step or multiple steps, the delta H is going to be the same. So if we really want the delta H for this blue reaction, but maybe it's hard experimentally to do that, maybe it's hard to actually get the liquid water, we can use previously established values. We can say, well, we know the enthalpy change for burning methane and getting gaseous water out. We used our bomb calorimeter, for example, and we figured that out. We also know the enthalpy change for water condensing, going from gas to liquid. And we can see that we're going to actually be able to combine those. And so we want to arrange our reactants and products so that when we add our reactions together, things will cancel out. And the important part here is that delta H for reaction 3, which is just, sorry, I'm going to sneeze again. I hate that. Don't you hate it when you like have that fake sneeze, or the sneeze is right there, but no. That this reaction, because it is, the reaction itself is made of these two reactions put together, that the enthalpy for this reaction will be the enthalpies for the two put together. But there's just one more bit here. If we go ahead and just add these, we'll add all our reactants and all our products. I'm going to add all our reactants. So I've added everything from reaction 1 and reaction 2 here. Well, we see here we have this guy is on both sides, but we don't have enough to get rid of it. And we don't see it in our final reaction, right? We don't see H2O gas in our final reaction. So remember, if things are just like in a math equation, if you have the same thing on both sides, they can be canceled out, right? If you have x plus 2 equals y plus 2, you can get rid of the plus 2's, right? You can just subtract 2 from both sides, and now you have just x equals y, or whatever. We can do the same thing with chemical components too. But if we subtract H2O gas, we're still going to be left with one H2O gas, right? And we know that in our final reaction, we want 2 liquid waters. So what we're going to need to do is we're going to need 2 of this reaction here. And so we can put some coefficients there. Aha! And now we see that since 2 H2O gas is on both sides of our reaction, we can get rid of it. So just like with, what did we do this for? We added things together and canceled them out before. Oh yeah, net ionic equations. Like, it's the same idea here. So if something is identical on both sides, you can cancel it out. And with this sort of thing, I'll be giving you, here's reaction 3, here's some potential reactions. See if you can manipulate those reactions in order to get reaction 3. And so in this case, we just had to multiply reaction 2 by 2. And then we could add them together and get this to work. And so how does delta H come in for these? Well, delta H reaction for our first reaction is negative 802 kilojoules per mole of methane, I suppose. So delta H for reaction 2 is negative 44 kilojoules per mole. But remembering that delta H does depend on the amount of substance you have, if we double our reaction, we need to double our equation. Hold on, I've got a Discord message. And apparently someone's lying to y'all. No, unfortunately this this video, as you'll be watching it, cannot be watched live because I don't know, that's the way it works. So, anyways, back to this. If our delta H reaction as written is 44 kilojoules, 2 times that reaction would be twice as much energy, right? If we take 1 mole of water vapor and condense it to liquid, that's 44 kilojoules. If we need 2 moles of gas to condense to liquid, that's going to be twice as many, right? Twice as much. So 2 times delta H reaction 2 is negative 88 kilojoules per mole. Hold on, I've got to deal with the Discord. You'll be able to watch it once it's uploaded. It's going to be up around 11:30 or so. Okay. All right. So you even get your little shout out on this video here, correct? So I'm responding to you still. So it's still live, right? So cool. So the idea here is that we're combining these two reactions. And in this case, we needed to multiply our second reaction by 2. And so, really, we're going to be using these two numbers here, because that's what we're adding together. Reaction 1, we left alone. We didn't need to do anything with it. Reaction 2, we had to multiply it by 2 to make sure that everything canceled out properly. And as a result, we've got to multiply our delta H by 2. And so, our delta H total for this new reaction is going to be the sum of those two. Notice again we use the 88 because we had to multiply our second reaction by 2. And so if we add these together, we get negative 890 kilojoules per mole. So, ta-da, we've done it. So without actually having to do an experiment, we can figure out what the delta H for this would be, theoretically speaking. By using reactions we already know the delta H of, or have figured out before, or something else. So Hess's law problems like these, I'll be giving you, 2, 3, 4 equations, and you'll be combining them in different ways. A few things I want to talk about delta H that we already have talked about before, and let's do these in dark blue. Remember, if you multiply a reaction by a coefficient, so if you need to add things together that you need more of, like we needed more waters in this case, delta H gets multiplied by the same number. And we'll see some more examples like that. So if we multiply a reaction by a coefficient, because we need to, because remember, delta H does depend on your how much reactant and all that you're actually using. And hopefully that's obvious. If you burn a small amount of gasoline, you get a small amount of energy. If you burn a lot of gasoline, you get a lot of energy out, right? But the ratio is still the same. That's why we standardize it. So if you need to multiply your reaction in order to get things to cancel out, your delta H gets multiplied as well. If you reverse a reaction, the sign of delta H changes. And so sometimes I'll give things to you that you need to switch the sides of. And we'll do some examples like that as well. So remember that for any reaction, the opposite reaction or process would just be the same delta H value, but the opposite sign. So for example, we saw that our condensing water is exothermic. If we want to do the opposite reaction, if we want to boil our water, evaporate it, it's going to be an endothermic process, and it's going to take the same amount of energy. So you can reverse a reaction if you need to, in order to make things work, and if you do that, you will have the opposite sign. So if you had a -1 originally, if you reverse it, it's now positive. If you started with positive and you reverse it, it's now negative. So just remember that the opposite processes will have the opposite sign. All right, so these are really the only two things we can do. We can multiply things by coefficients, or we could reverse the order of the reaction. And by doing so, we just do small changes to delta H. All right, so I'm going to give that a second to process. Well, I guess this is on YouTube, so you can just pause it. Yay. So in that case, I'm going to just keep going. So pause it if you need to, take a break. Let's see some examples. I've got some more here. These ones I can't just make up, so I'm going to use all the ones from the book here. So here's one for us. So here's carbon plus half an oxygen. You're going to see that halves are going to be pretty common with these Hess's Law problems. This will give us, actually that's a half a carbon. Oh, I'm sorry, this one does not have a half. And we've got delta H is equal to -393.5. And another reaction is if we have carbon monoxide. Oops, it's totally not that. We can also make carbon dioxide, right? So this is an interesting problem to look at. I'm just writing the numbers out first, and I'll explain the problem in a second. -283.0. Okay. I want to find out what happens to get to carbon monoxide. So this is an interesting idea because sometimes, well, yes, we just use Hess's law for convenience. Sometimes it's experimentally impossible to figure out something. For example, figuring out how to get from carbon and oxygen to carbon monoxide. That's not something easy to do because very often that first reaction happens. If you burn charcoal, you get carbon dioxide as your predominant product, like 95% or more, right, is carbon dioxide. So if you want to figure out how much energy it's going to take just to go to carbon monoxide, that may be troublesome. But if we know how much energy it takes to go from carbon to carbon dioxide, and the amount of energy from carbon monoxide to carbon dioxide, we can kind of piece these bits together to try and figure this out. So, what's a good way to approach these problems is to look at your final reaction, see what your reactants and products are. And then take a look at your given reactions that you're going to be combining and see what sides of the reaction those are on. For example, we see in our products we have carbon, oxygen as our reactants, and then we have carbon monoxide as our product. In our first reaction, I'm going to underline our reactants in light blue. So these are our reactants. So I'm going to underline all of those in our equations here. And we also know that we have a product. And so we'll find that in our reactions as well. And so if we just leave these reactions alone and add them together, we get C plus, I guess, 3/2 O2 plus CO turns into 2 CO2. That's not what we want, right? If we just add them as is. Notice we want carbon monoxide as a product. That tells us that we have to flip that reaction around. We can't use it as is because that'll give us carbon monoxide as a reactant. We want it as a product. So we're going to need to invert that reaction. And so let's rewrite it here instead. And the delta H for this would just be positive 283 kilojoules per mole. And so we can kind of say, okay, we're not going to use this one anymore. Let's see if we're all good with this one. Do we have carbon as a reactant? We do. Let's worry about oxygen in a second. Do we have carbon monoxide as a product? We do. So that's the good part. Oxygen here we have both as a reactant and a product. But if we look at our oxygens, we have 1 oxygen and a 1/2 oxygen. What we want is 1/2 oxygen. And if we think about this, we're going to end up with oxygen on the reactant side, 1/2 oxygen on the product side. So overall, that's 1/2 an oxygen on the reactant side. If we subtract 1/2 oxygen from both sides, we do end up with 1/2 of an oxygen on the reactant side. And we notice we have carbon dioxide also on both sides. Those two will cancel out. And so if we write the whole thing out, I'm going to do that for this problem. Some of this is kind of guess and check. It's like, okay, I'm going to add these together and see if I've done enough with these reactions to get them to cancel out whatever I need to cancel out. CO. So right away we can cancel out the CO2s. And let's subtract 1/2 O2 from both sides. So 1 O2 minus 1/2 O2, that equals 1/2 O2, right? Oh, that's it, actually. Right, so if we do that, this cancels out, right? 1/2 minus 1/2, 0. 1 minus 1/2 is 1/2. So as a result, we get this, and is that indeed our reaction that we want? It is. And so now we just have to look at the delta H's and see, aha, what did we do? All we had to do was switch around the second reaction. So we just need to make sure to use the positive value of delta H for that one. We're going to still use the same one for the first. So as a result, we can say, aha, well, delta H3, the one we're looking for, is delta H1 plus delta H2, whatever reactions we added together. Our first reaction, we didn't change anything, so negative 393.5. Yes. All right, plus 283. Remember, we always use the delta H for what we actually used. We used the green reaction. We canceled out that other one. We flipped it around because we needed to. So we're going to use plus 283. And doing this, We have 393.5, 283. So we get negative 110.5 kilojoules per mole. Ta-da! So for something experimentally that we can't do, because it just wouldn't work, we would end up just going to CO2. We have ended up with what we wanted. So that is how we can calculate delta H for this reaction. And we're going to see sometimes you'll need to do more than one thing. In the last problem, we had to multiply one reaction by 2. In this problem, we had to reverse one reaction. Sometimes you'll need to do multiple things. And you can multiply by whatever you want, as long as you also multiply delta H by that number. So, let's do another one. Let's see here. What do we want to do? How about we do this one? Okay. Here's another one for us. I want I want 2 carbon turning into acetylene. Is this gas or liquid? It's gas. Okay. I want delta H for this reaction. Here are the ones I have. So I've got acetylene burning. Easy to measure, right? We can burn things. We have 5 halves O2. Yes. Turning into 2 carbon dioxide. And liquid water. Alright, that's one reaction. Delta H for this is negative 1299.6 kilojoules per mole. I'm going to need more space on these. Next one we have is just burning carbon itself. We've got carbon dioxide, delta H for that. We just did negative 393.5 kilojoules per mole. And one more, we've got burning of hydrogen. So all of these are easy reactions to do. Right? Combusting things, pretty standard. Things that are very easy to do in a calorimeter. We can burn things and get their delta H values. Speaking of which, that one is negative 285.8. So, another thing, remember, 3 reactions this time. A good thing to do is identify in our given reactions what we need on the product side, what we need on the reactant side. So let's do, I'm going to use again the same colors. I better check what those are. I use blue for reactants. Okay. So I'm looking for these 2 things to be reactants. I need carbon, solid, and I need hydrogen, gas. So, we've got those. So I need carbon, solid, and I need hydrogen, gas as my reactants. Looks like those are already on the reactant side of these equations. So that's good. The product I have is acetylene, C2H2. You don't need to know that name yet. That's a reactant, right? So, or it's a product, but here it's a reactant. So we need to reverse this reaction. Right? Because we need it to be on the product side. If we look at the rest, we also see that in our total reaction, we have 2 carbons. Solid. But in our given reactions, we only have 1, which means that we need to multiply this reaction by 2. We're doing both of them together this time. And the third one, it looks like we can probably just leave that alone. So let's try doing these things and try to add them up. So if we reverse the reaction, I'm going to just write that one here. Two carbon dioxides plus water turns into C2H2 plus 5 halves O2. Okay. Now let's try adding these 3 up and see what happens. And I'm going to still multiply this other one by 2. I guess we should do that. No. Go away. Okay, there we go. So let's try putting these together now. So I'm going to add up everything that's in the purple box here. I'm going to add up this stuff. These are the reactions that we think should work based on where we found our reactants and products and any coefficients that we needed. We're going to try adding these together and seeing if it all cancels out. All right, looks like a mess, but what we did again, we took a look at what's in our products and reactants for the reaction we want, found all those bits in our given equations, and adjusted our given equations so that we have all those components. And generally speaking, that's enough. But let's make sure. Sometimes it might not be. So if we add this up, 2 carbon plus 2 O2, I'm going to put all our reactants on one side, plus H2. We have a half oxygen here, plus 2 CO2, plus H2O. So, that's all of our reactants. Let's do all of our products, and I'm going to do them in a different color so we can see. We've got 2 CO2 plus H2O plus acetylene plus 5 halves O2. So what you'll want to do is combine like terms so everything is very clear. Right now that means that we need to combine this half oxygen with this 2 oxygen. That gives us 5 halves. Right, 2 oxygen is 4 halves. Add 1 more is 5 halves. And let's see what's the same. Well, we've got 2 CO2s, H2O liquid, 5 halves oxygen. That all cancels out. So we're left with 2C plus H2 turns into C2H2. And indeed, that is the reaction that we want this for. So let's go ahead and now deal with all our delta H's. So this delta H is going to be the sum of the 3 reactions. Our first one we multiplied by 2, so I'm going to just do the order we added them. So the blue one is for what used to be reaction 2 is our first one. So we have 2 times negative 393.5. Great. Second one we left alone, so we can just leave that up. Negative 285.8. And then the last one we had to reverse it. That's the reverse of our original reaction, which means that's a positive one now. So that was 1299.6 kilojoules per mole. I forgot the moles there. So there we go. Now we just need to add them up. And so we can do this. So 2 times negative 393.5 plus negative 285.8 plus 1299.6. Doing this, we get positive 226.8. Thankfully, all these numbers had 1 decimal point, so our answer still has 1 decimal point for sig fig purposes. And so this reaction here has a positive delta H, so it's endothermic, and that's the value for it. All right, so it's really essentially the same process we do over and over. And so we just need to keep in mind what we do to each reaction. So our first reaction in the purple box, we multiplied it by 2. So delta H gets multiplied by 2. The second one, we left it alone. The third one, which was the reverse of our other one, the other one had negative 1299.6. We reverse it, so it becomes positive 1299.6. All this stuff about 1, 2, 3 is all arbitrary. I could set whichever one I want to be delta H2. I could set our first one to be H3. I could set our third one to be H2 and our first one to be H1, whatever. It doesn't matter. I mean, it's adding. 3 plus 2 plus 1 is the same as 1 plus 2 plus 3. Right? It does not matter what you give these arbitrary things to. The point is you add up the delta H's for everything that you used to come up with your equation of whatever I'm asking you to do. Okay? So that's Hess's law. So for any reaction or process that you know the delta H of, you can combine them together, hopefully canceling things out, so that you can end up with a new equation that you can calculate delta H for theoretically. And again, this is for things typically that are harder to do experimentally, or if we already have the data, why reinvent the wheel? We can just use math instead of having to do a whole experiment. So we're going to do now the next thing, which is more of Hess's law, but in a special case. We're going to see that many compounds have established what are called standard heats of formation. Oops. Which is abbreviated delta HF. And that little degree symbol up there tells us it's a standard. So a standard for 1 mole of that substance. And what these are, a formation reaction takes all of the elements in a compound it tells us the delta H for this reaction. For example, delta HF for water would take the elements in their standard state. Both hydrogen and oxygen are diatomic. And we would say that this would be our value for HF. This is the reaction that would be HF. And the value for this is negative 285.8. Delta HF always tells us the amount of energy needed to make 1 mole of our product. These are all for 1 mole of product. So that's why we're going to see all these halves and things in our reactions, which is totally okay, because we're interested in standardizing this to our moles of product. And we're going to see how this is going to become easy for us to figure out reactions for. We can figure out delta H just by looking at these established values. Another thing we can look at, let's say, how about delta HF F for methane. The reaction for this, to form methane, you're looking at what elements make that up. For carbon, you're going to see that carbon's standard state is graphite. We need 2 hydrogen molecules, and we'll make 1 mole of methane. So it's just taking each element that is part of a compound, putting them together in their standard states. I'll show you a table for all that. And this one happens to be, I hope it's on this list, it is negative 74.8. And let's do another one. How about delta HF for, how about we do glucose? If we think what elements do we need to make glucose and what are their standard states, we need 6 carbon. Graphite is the standard state for carbon. Plus, we need how many H2s? We need 6 H2s. Remember, hydrogen always comes as diatomic. And standard state means their kind of state of matter and form that you'd find these elements in nature. So, for example, sodium you would find as Na solid. Carbon you find as graphite, as opposed to diamond. You don't find diamond as the standard state of carbon. Oxygen you find as O2. Chlorine you find as Cl2. Silicon you find as Si. Most elements, as we know, are monoatomic. Carbon's a little special. It has allomorphs, graphite and diamond and fullerene, but we don't really worry about the last one. Putting these all together, we would make our glucose. And do we have this one? Oh, we do. Lucky us. Delta H for this is negative 12.73 kilojoules per mole. It's time to show you something. In Discord, I'm going to move this over here so we can see it. In Discord, in our extra resources tab, I am going to post this again so we all have it. What this web page is, oh my, I'm going to make this a little smaller. Oh, it's terrible. Regardless, what we're looking at is this table has delta HF values for many substances. So if we look at some of these, we have graphite, we have diamond, we have carbon as a gas, methane, methanol as a gas, carbon dioxide, cesium, I don't know, iron, solid, lead, whatever. We have all these different things. So I'm going to be able to give you all sorts of different equations on your homework that that you'll need these for. So, you know, if you need to look up the heat of combustion of methane, it's here for you. I'm sorry, that's not methane, that's ammonia. And so you'll be able to find all these fun things. Okay, so that's in Discord. It's also on Canvas. I've put it as, instead of using Appendix C if you don't have the book. This Appendix C has the same values in your book as this table does. So I think it's just a little bit easier to use the web page. But if you like to flip back and forth in your book, that's fine too. So the purpose, though, of doing this is that we can use these to figure out reactions easily by using common compounds that have established values. We're going to see that, let's see, do we want to do an example of this? Let me find an example for us. Okay, let's take a look at this. Here's one we're going to use propane and burn it. We're going to calculate this. So here's an example of what to do with these heats of formation. C3H8 plus, how many oxygens do we have for this? 5. Oops. Three CO2s plus, what do we have? Probably 4 waters, yeah. Are we doing liquid or gas here? Liquid. Okay. So, what we can do with all of these is break them all down into their elements. I could write all that out, or I could just make this a little bit easier for you. We're going to see that delta H for a reaction is your products minus your reactants. Makes it a little bit easier this way. These technically are sums, so add up all your delta H's for your products and all your delta H's for your reactants. I'm going to redraw that because that's ugly. And so, if we really wanted, we could split up the carbon and hydrogen in propane, and we could do all the same for all these compounds. And we're going to see that all those elements would cancel out, except for the ones that we need here. So, easy way for us to do it is to just understand this. The formation of our products minus the formation of our reactants will give us delta H for any reaction. And so we just need to consider, okay, well, what do we have here? We have, in this one, for this particular reaction, we're going to need 3 times the delta HF of CO2. Why do we need 3? Because there's a 3 in our reaction. Delta HF tells you 1 mole. So if we need 3 moles, which our coefficient is, we need 3 of those delta HFs. We're going to also add our delta HF for water liquid. These are all of our products here. We're going to then subtract the delta HF for propane and 5 times the delta HF for oxygen. We're going to see something special about oxygens that's going to make it, again, a little bit easier for us in just a little bit. So, if we look up these values, we have, what did I say? We have CO2. Okay, carbon dioxide. Again, I would expect you guys to use the web page. Actually, fine, I'll show you how. We'll do that. Here we go, web page again. So we have CO2 is our first one. We're going to make this a little bigger. So CO2. So we're going to find carbon. We're going to find CO2 gas. Aha, here it is. 393.5, negative 393.5. So moving this aside. So our first one is 3 times negative 393.5 kilojoules per mole. Plus 4 times water liquid. So we're going to find water liquid. We're going to go to oxygen. And here's water liquid. So 285.8. I feel like these are all numbers we've used before. So 285.8 kilojoules per mole minus delta HF for propane. Let's scroll up to carbon. We're going to find propane. Here it is, negative 103.9. So remember we have a minus sign here, negative 103.9. I hope that's what it said. I need to check that again because I think I forgot the number. 103.9. Okay, we're good. And the last one we have, kilojoules per mole. I'm just gonna keep the minus 5 times 0. This is something special. If you look up oxygen, you'll find that it's 0. And so, doing this, 3 times negative 393.5 plus 4 times negative 285.8 plus 103.9. We do all this, we get negative 2219.8 kilojoules per mole. And thinking about it, does this number make sense for us? Probably, because it's a combustion reaction. We would expect this to be producing a lot of heat, so it's a high negative number. Or rather, I guess a low negative number. But in magnitude, it's a big negative number. So highly exothermic. Makes sense for us. Note, for any standard element in standard state, 0. Because we already have it, right? We use these. We use delta H to describe formation of these things. If it's already O2, there's no formation necessary. It's already O2. So for any element in your standard state by itself, delta HF is just 0. So I wrote that we would need 5 times that, but since it's just 0, we can ignore it. So I'm cool on your homework if you just say, well, this is just oxygen. This is just hydrogen. I'm going to put 0. You don't even have to look them up. But I'm going to prove to you that I'm not lying. Let's get up our table again. Notice carbon for graphite. So if you don't know what your standard state is, you'll see it has a 0 on this table. Calcium solid. Bromine 2 liquid. Beryllium solid. Barium solid. Aluminum solid. What are we looking up? Oxygen, I think? Yeah, oxygen. O2 gas, 0. So, standard states have a delta HF of 0. Again, everything we're looking at in this class is this first column. This is the one we're looking at. If you take 113 next semester, we'll use the other two. But right now, we're just using delta HF. All right, so these are standard enthalpies of formation. All right, and these aren't terrible. We can use them to calculate almost any reaction we wanted. Why don't we do, how about we do an acid-base one? Let's see what happens when we put, let me just make sure that we have all these. Let me see if sulfuric acid is on here. We do have sulfuric acid, okay, and do we have potassium hydroxide? We do. Okay, perfect. What's the other one? K2SO4. I hope we have K2SO4. We don't. Let me just Google it. Let's see if we have it. Delta HF potassium sulfate. Did we get a number? K2SO4. Oh, the problem is I'm getting see people using hydrofluoric acid. So just give me the freaking number. I could make it up. No, enthalpy of aha. No, this is dissociation. Oh, damn it. Okay, I'm just gonna make up a number for K2SO4 because why not? Oh no, we're good. I found one. Oh, this is solid though. Oh, give me K2SO4 aqueous. You can do it. Come on, computer. Okay, let's just, I'm gonna do some calculation real quick in my head. So that was, what was the dissolution? 19. Okay, so then we'll just say this one is negative 1412 kilojoules per mole. I'm making this number up. All right, so I'm going to tell you that one. So this is delta HF for this compound. The rest of them are given to us on our chart. So on your homework, everything that will be there will be on the chart. So this one just didn't particularly happen to be there. So for this reaction, we're looking at products minus reactants, right? So we need 2 times delta HF water plus delta HF for K2SO4 aqueous. Again, that's the number I've made up because that one's not on our chart. We're going to subtract delta HF for sulfuric acid. And we're going to subtract the delta HF twice of that for KOH solid. All right, so our products minus our reactants. And I just put them on separate levels, so it's very easy to see the pluses and the minuses. All right, either than that, you can add them both up and then subtract them. So, cool. Let's look these numbers up. So 2 times for water, we've done this 15 times. We have the number here, 285.8. Plus 2 times the potassium sulfate one, which I've... No, not 2 times, just regular. Negative 1412 kilojoules per mole. I'm going to put a 0.0 just for sig fig purposes. That's the number I've made up. This is, as you'll see. We're going to subtract sulfuric acid. This one we are going to have to look up because I'm going to do that. So sulfuric acid. Actually, we have KOH here. Let's just write that one down. So later on, we have 2 times that number. So since we're already here, I'm going to write it down. Negative 244.7. Okay, and then sulfuric acid. Let's find you. Negative 909.3. All right. Here we go. We have the numbers. So, hardest thing on this is dealing with the positives and negatives. So, just make sure you got all those right. So, 2 times negative 285.8 plus, or rather minus, 1412 plus 909.3 plus 2 times 424.7. Overall, we get negative 224.9 kilojoules per mole for our reaction. Ta-da! So, we can use it for any reaction. The theoretical ones are easy. We just got to look up their numbers, plug them in. So, that's really it. We're luckily, that's all we need to worry about with these. We can do one more. What shall we use? How about we do some... Let's burn some sucrose. All right. Oh, but never mind. We're going to have to balance this. I don't want to do that. Actually, I'm just going to Google it because I don't want to balance this equation, but I'm sure it's been done before. Okay, let's see. Perfect. Oh, wait, this is an easy one, actually. So we need 12 oxygens. Turns into 12 CO2s. Plus 11 waters. There we go. Let's figure this out. Well, using adhesive formation, we can do this, right? We can say, aha, well, we've got CO2. We need 12 times the CO2 plus 11 times the water. Don't forget your states of matter, because those do change things. We have -1 times delta HF of the sucrose here, minus 12 times delta HF of oxygen, which is a 0, so who cares? I'm not even going to put it. Nope. So remember oxygen, standard state already, don't worry about it. This is 0. So just got to look these numbers up, and in fact the CO2 and water we already have. 385 point something. Aha, 393.5. Plus 11 times water's was 285.8. Look at how efficient we are. We already have these numbers. And we're going to subtract sucrose's, which is negative 2221 kilojoules per mole. I'm just not even putting the units because shame on me. The unit will be kilojoules per mole at the end. If we need to look up sucrose, we would go to our chart. I mean, I had the number in the book, but I'll show you all on the chart. We got to go up to carbon. Apparently this chart doesn't even have sucrose, but the book does, so we'll just use that. It is glucose though, but not sucrose. All right. Anyways, here we go. 12 times negative 393.5 plus 11 times negative 285.8 plus 2221 equals negative 5,644.8 kilojoules per mole. Very, very exothermic reaction. This is what our bodies use, right? If we are eating sugar. If we eat a mole of sugar, which is 360 some odd grams, or 300, yeah, it's about 360 some odd grams. That's a lot of sugar. You'd end up getting this many kilojoules out of it. Although our body can only use about a third of the energy, so yeah. So the calories that are actually reported are not as much. So, anyways, that's irrelevant. So the point is, with this, with heats of formation, you can just look up numbers on a chart. As long as their equation is balanced and you have your states of matter, you're golden. And generally speaking, your states of matter will be given. So it's really balancing, maybe. I don't even remember on the homework if it's balanced for you or not. So shouldn't be too bad. All right, so that's the end of thermochemistry for now. We will talk about it one more bit in chapter 8 or 9, somewhere around there. We're going to talk a little bit more about thermochemistry. But that's it. So we found delta H can be done experimentally, or it can be done theoretically, uses Hess's law or the heats of formation of your compounds. So have fun. I'll go ahead and upload this for you, and we'll just end this here. So a little bit shorter of a video today, but I guess that's a good thing, maybe. Alrighty. That's that then. Take care, everybody.